Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about the finite volume method in CFD. To give you an overview of what I'm going to talk about in these slides, I'm going to start with looking at how does the finite volume method work. Then I'm going to look at what are the differences between implicit and explicit treatment of various terms. And to finish off, I'm going to look at why is a special treatment required for the convection and diffusion terms in the finite volume method. So to start things off, we have the Navier-Stokes equations there in equation 1, and what we would like to do is we'd like to write these partial differential equations in matrix form given by mu equals b there in equation 2, where m is a matrix of coefficients, u is the unknown velocity vector, a velocity for every cell in the mesh, and b is a right hand side term. And once we've written our Navier-Stokes equations in this linearized matrix form, we can use a variety of linear equation solvers to solve for the velocity field in an iterative process. So the topic of this talk is how do we convert the Navier-Stokes equations there in equation 1, which is a partial differential equation, into matrix form, and we're going to be using the finite volume method for that. And for demonstration purposes here, I'm just going to be considering the steady, incompressible Navier-Stokes equations, and this process can be readily extended to compressible and unsteady forms of the Navier-Stokes equations. And the discretization I'm going to be using here is a general discretization for a 3D polyhedral cell. That's a cell with m sides, where m is an integer. It doesn't have to be a cuboid. This same treatment can apply for prisms, tetrahedra, and quadrilateral and cuboid cells that you might see in a mesh. And so the advantage of using this generalized finite volume method is that there are no restrictions on the user over what type of mesh they can create. They can generate any type of mesh with polyhedral cells, and the same method can be applied to discretize those equations over the cells. So in the second order finite volume method that we're going to be considering here, the flow variables, that's pressure, temperature, velocity, turbulent kinetic energy, these values are going to be stored at the cell centroid. And this is a cell-centered finite volume method that's used by codes like OpenFOAM and ANSYS Fluent. And the flow variables are stored at the cell centroid, and they're assumed to vary linearly across the cell. So between the cell centroid and the various faces of the cell, they're going to vary linearly. And in this treatment today, we need to consider the owner cell, that's the cell we're looking at, with a cell centroid P, and this cell is going to be connected to various neighbor cells which have cell centroids N, and the flow variables in those cells are stored at their cell centroids there. And again, because we're using a polyhedral cell that may have m sides, then our owner cell P is going to have m neighboring cells which are connected by m faces. So now we've set up, we can start looking at the finite volume method itself. So to start, what we do is we integrate the entire Navier-Stokes equation across that owner cell P. And so we take the equation and we integrate it across a volume there, that's equation 4. And of course, integration and addition are commutative operations, which means we can split up the various terms and integrate them one by one. And this will make it a lot easier for us to explain and understand what's going on. And we're going to consider each term separately, as each of the terms is going to require a slightly different treatment in order for us to integrate them. And in equation 5 there, you can see we've got the convection term on the left, then on the right hand side we've got the pressure gradient, the diffusion term, and some source terms. And just as an example here, I've put the acceleration due to gravity as the source term. To start things off, we're going to be looking at the source term as it's the most straightforward. And if we have a constant source term, say acceleration due to gravity g, then that source term is constant across the cell, and of course we pull it outside the integral, and so we get the finite volume integration is g multiplied by vp. That's the volume of the cell which is stored at the cell centroid. And now if we think back to the matrix form that we're considering, that's mu equals to b, then equation 6, g multiplied by the volume of the cell, doesn't depend on velocity at all. So in this case, the source term gets added as a contribution to the right-hand side of equation 7. That's the b vector. Whereas anything that's going to be proportional to velocity is going to be added to the matrix of coefficients on the left-hand side. So the constant source terms, such as gravity, are easy and straightforward to take care of. But what happens if we have a source term that linearly depends on velocity? Say, for example, if there was some source term SU added to the right-hand side of the Navier-Stokes equations, a general source term where S is some scalar. These types of source terms are fairly unusual for the Navier-Stokes equations, but for other scalar transport equations, such as turbulent kinetic energy and temperature, these source terms are more common. And so the treatment doesn't depend on which equation we're using. We use the same process to integrate these source terms across our cell. And so what do we do for our linear source term? Well, the integration is a little bit more involved now, and we have to pay close attention to ensure that we understand what we're doing. So we start with equation 9. We've got S, which is some scalar, some constant, multiplied by velocity, and we're integrating that over the cell. So it's a volume integral there in equation 9. And the first thing we're going to do is we're going to take that scalar, that's constant scalar SP, outside of the integral. And then what we're going to do is we remember that because we have a second order finite volume method, the velocity varies linearly across the cell, as will the temperature and the pressure and turbulence and all the other fields. And so we expand the velocity u, given there in equation 9, to give equation 10 there. So we've said that the velocity variation across the cell is given by up, that's the value at the centroid, multiplied by adding the distance between some point in the cell x minus the cell centroid xp. So that's the distance vector multiplied by the gradient of velocity at the cell centroid. So that's grad up there. So we've expanded velocity to give the linear variation across the cell. And now moving to equation 11, we're going to split those two parts to give us two integrals. So the first part is going to be SP multiplied by the velocity at the cell centroid. Up is a constant, and so we can bring it outside the integral. And then for the second part, we can also take the gradient at the cell centroid outside the integral. That's grad up there, and that just gives us the remaining integral of the position of every point in the cell relative to the cell centroid. Now, this integral here is actually 0, and this follows because that is the definition of the cell centroid of a given cell. The cell centroid xp will always satisfy that integral there. So if we can think of this physically, what it means is that the distance from every point on the cells to the centroid, if we average those, then the integral is 0, and that's why it's the cell centroid. So equation 11 there simplifies down to SP, that's our constant scalar, multiplied by the velocity at the cell centroid, multiplied by Vp, which is the volume of the cell. So that's our linear source term. And now if we think back to our general matrix form, mu equals b, we've got a term that's proportional to the velocity. So because our source term was on the right hand side, if we moved it to the left hand side of the equation, then we can see that we'd be adding a contribution minus SPVP to the M matrix this time, so left hand side matrix. And this is different from that constant source term, that gravity term, which we added to the B vector on the right hand side. And at this point, we should always point out that we don't have to add the SPVP contribution to the left hand side matrix. We could add it, we could add the entire term SPUPVP to the B matrix instead. So there are two different treatments that we have for source terms. We can add them to the left hand side as implicit terms, or we can add them to the right hand side as explicit terms. So how will this look? So if we add to the M matrix, we're going to be getting a diagonal contribution of minus SP times by VP. And it's a diagonal contribution because it's the cell centroid of the cell that we're currently looking at, whereas the off-diagonal terms are related to the neighbouring cells. So that's how the M matrix would look, and the B matrix, if we chose to use an explicit treatment instead, would look like SP UP multiplied by VP. And for each of these source terms, CFD codes will often choose on the fly whether to use implicit or explicit treatment. And the reason we might choose to use an implicit treatment is we want to try and increase the diagonal dominance of the M matrix, because this makes the matrix more stable. So if we're going to be getting a positive contribution to those diagonal terms there, so if S1 is negative, then we would choose an implicit treatment because we'd increase the diagonal dominance. However, if the S term there was positive, that will be reducing the diagonal dominance, and so we choose an explicit treatment instead. So the treatment of source terms will depend on whether we're going to be improving the diagonal dominance of the system or not. Now, what about other source terms? If we have a source term such as SU squared, for example, and this type of source term you'll see in the dissipation equation in the K omega model. There's an omega squared term as a source term. We may have cubed or other source terms as well. How do we deal with these more general source terms? Well, what we usually do is we try and linearize the source term. And the way we do that, you can see there, going from equation 17 to equation 18, is we rewrite that as S multiplied by, in this case, U from the previous iteration. So the velocity is lagged, and we know what this velocity field is, multiplied by the unknown velocity. And so if we were to carry out the integral, because the velocity from the previous iteration is known, that's then agglomerated together with that SP term, and we can calculate the integral there to give us SP multiplied by UP for the previous iteration multiplied by our unknown UP. So this sort of mixed implicit explicit treatment, we will then evaluate whether that term gives us a positive contribution to the diagonal dominance or a negative contribution, and then the CFD code will decide whether to add it to the left hand side or the right hand side of our matrix equation. And if we were to have a cubed term, say, then it would be S multiplied by the velocity from the previous iteration squared, again leaving that linear contribution there, which we'll use in the integral. So that's mixed implicit explicit treatment for source terms. How about the convection and the diffusion terms? So when we think back to our Navier-Stokes equations, these terms are a little bit more tricky, and the reason for that is because they contain the divergence operator there, which you can see in equation 20. So we're going to have to do something slightly different if we want to integrate these terms over the cell volume. And in this talk, I'm only going to talk about the convection term because the diffusion term is a little bit more involved, and I'll do that one in a separate video. And the way we integrate the convection and diffusion terms is we use the divergence theorem. And what the divergence theorem says, if you can remember back, that the integral of the divergence of any general vector field f over a volume can be expressed equivalently as a surface integral. So those volume integrals which we had for our cells in the Navier-Stokes equations, we can rewrite those as surface integrals. And the surface integral there says that we're integrating the dot product of that vector field f and the unit normal vector on the surface, and we're going to be integrating over the entire surface of our body, and in this case our cell, because we're using a CFD mesh. So we're going to be using that divergence theorem to modify the convection and diffusion terms and work out the integrals. So if we use the divergence theorem on the convection term, that nabla.uu, then we arrive at equation 22. And what we've now got is a surface integral over the surface of our entire cell of u, the velocity field, multiplied by u dot producted with the unit normal vector on the surface of the cell at that point, and then integrated over the cell. And if we take a minute to think about what this physically represents, the term in the brackets, that's u dot n times by the element of surface, this is actually the volume flow rate out of the cell at that point. So n is the normal vector pointing out of the cell, and so the dot product with velocity times by the area is the volume flow rate out of the cell. So we can think of this integral as the volume flow rate out of the cell, which is convecting the velocity field with it. And that's really what the convection term shows us. So now we've written the volume integral in the form of a surface integral. Can we make any further simplifications? Because we need to linearize this term. The trick that we do now is we remember that we have a cell with a finite number of faces. So we may have an m-sided cell, it could be a tetrahedra, a hexahedra, or some kind of polyhedral cell, but we have a finite number of faces. And so what we do is we replace that surface integral by the summation of the surface integral over all of those individual faces there. So what we would do is we'd go around the cell, and for each of the faces work out the integral over that face of the convection term there. And can we do any better now at this point? Turns out we can. What we now do is we make an approximation, and the approximation is for the integral over each of those faces, that the integral can be taken as the value at the face center. That's u sub f there. So rather than integrating the velocity and the volume flow rate over the entire face, we're just going to take the value at the face center. And there's actually a proof of this simplification, and you can find that in Professor Jasak's thesis, which I'll link in the description below. But once we've made this approximation, we notice that the integral is now gone. All we have is a summation of terms, and the summation is over each of the cells, each of the faces on that cell. So if we had a hexahedra, it would be a summation of 6 terms, for example. And what we're doing is we're summing the product of the volume flow rate out of that face center multiplied by the velocity field at that face center. However, if we think back to how we've set up our cell-centered CFD code, we know that the value of the flow variables, velocity, pressure, temperature, is only stored at the cell centroids. So for our owner cell there, owner cell P, we know the velocity at point P, and then for the neighbor cell across one of those faces, we also know the velocity at that cell centroid, but we don't know the velocity at the face center F, which you can see there in the diagram. And it's the velocity at that face center that we need in order to work out the summation of these convection terms. And this process will be repeated for every owner cell and neighbor cell that surrounds our cell P there. So it's quite clear from looking about this diagram and thinking about it that what we need is some form of interpolation. If we can take the value at the cell centroid P and then the value at the neighboring cell centroid N and perform some type of interpolation to get our face value there, F, then we can work out the convection term there. And it turns out that CFD codes provide a variety of interpolation schemes to calculate that face value, and I've covered these face interpolation schemes in a separate video, particularly looking at upwind differencing, central differencing, and linear upwind differencing. And so really, when you're setting up your CFD code and you're choosing a discretization scheme, really what you're choosing is the method of interpolating the flow variables on the cell faces, given that we know the values at the cell centroids. And at this point, if you haven't seen that video, I'd highly encourage you to go back and have a watch, and you'll soon understand how the different face interpolation schemes are set up. So just as a reminder, we can rewrite that volume integral of the convection term as a summation over the faces of the velocity field at the face center multiplied by the volume flux FF out of each of those cell faces. And it's quite common in textbooks, derivations and user guides to see the convection term written in that form there. But now that we've got that, equation 25, we would like to add the contribution of those convection terms to our matrix. That's mu equals b. And at this point, we can assume that the face center value we've computed from some combination of the owner cell centroid P and the neighbor cell centroid M using some type of face interpolation scheme that the user will choose. And then we can add those contributions to the M matrix. And how will this look? Well, the convection term is going to lead to diagonal and off-diagonal terms in the M matrix. And the diagonal terms are going to be given by the contribution of the owner cell centroid P, and then the off-diagonal terms are going to be given by the contribution of those neighbor cell centroids N to the face interpolation of the velocity field. And so when we look at that contribution to the M matrix, then the number of faces that our cell has is going to give the number of entries there across the row and across the diagonal, because the number of terms is a reflection of the connectivity of the cell. So a cell with 6 neighbors, say a hexahedral cell, will have one value on the diagonal and then 6 off-diagonal terms that represent the contribution of each of the neighboring cells to that cell centroid. And at this point, you may have noticed that we've been gathering multiple contributions to the M matrix and the B vector from each of the terms. And simply what we do is we add each of those contributions together until we have an overall mu equals b matrix set. And then we can solve that equation for the velocity field using an appropriate iterative solver. Just to summary, to wrap up of what I've talked about today, the individual terms in the Navier-Stokes equation are integrated over the cell volume individually, and each of these integrals give us different contributions to the M matrix and the B vector. As an example there, I've put the convection term, and then what we do is we add those contributions up and assemble our complete mu equals b matrix equation, which we can solve using an appropriate iterative solver, such as an algebraic multigrid method, for example. And the diffusion term is very similar to the treatment of the convection term. We use the divergence theorem for that. However, the manipulation is a little bit more detailed, as we have to consider orthogonal correctors. I'm going to go through those in a separate video. And for those of you who'd like some further reading, there's some useful information on the ANSYS Fluent user guide, and the section you want is section 25.3.1. And another excellent reference is Professor Jasak's thesis from Imperial College London, which really goes into the details of the finite volume method and deriving each of these terms in a lot more detail than I've considered in the slides here. And at this point, I'd like to once again thank you all for watching this video, and thank you for leaving your comments and error spotting in the description to the videos. I really appreciate your feedback. And as always, if you like this video, or if you have any suggestions for other videos you'd like to see me do, or something that you would find particularly useful, please just leave that in the comment section below, and I try to get to the comments as soon as possible and address them. And I'd also like to remind you guys as well that if you'd like some further information on some of the slides and material that I've presented here, I would head on over to my website, and there's a link in the description below to that website, where you can find summary notes and equations for slides that I've been through here. So if you really want to just quickly dive in and find the equation you were looking for, or look for that bit of derivation, but you don't really want to scroll through and scrub through the YouTube video, you can find all that on my website as well. Thank you very much for watching, and I look forward to hearing from you.